Um, yeah, so let's talk about preparation to deploy. And today we will talk about first about mixed precision and mixed precision training, then about tensor RT, which we will need. So the first thing is mixed precision, and maybe you've heard about that, that nowadays people try to make operations in FP16. And actually, if we talk about contemporary models such as LLMs, so like Llama and others, they all used mixed precision. Well, chances are that it's not the final point of this improvement, because even in FP8, people can train neural networks. And if we consider H100, new graphical card from NVIDIA, new top graphical card, so this is next after 800. So yeah, this H100, it supports FP8 instructions out of the box. So hardware engineers and well, their planning, it is pointed towards that thing. So I think in several next years we will see FP8 usage. And so what's the point of that FP? We save memory and we save computations, both of them, so that we can we can make bigger batches, we can make bigger networks. So twice as much computations is really, really good. But the thing is, so by the way, for graphical card, the native precision is 32. So graphical cards are designed to process FP 32 numbers, and not 64 bits, because 64 is already too much for such computations. It's not a big problem in CPU, but it is harder to implement in GPU because you need well, twice more memory, so it's crucial. Yeah, but the thing is that mm, n- not not in every command we can use FP16. Sometimes we need to use FP32, and we will see examples of such things further. Um, um, if we apply that thing, so we can have better computations. Also, we can, well, make bigger batches and so on and so forth. Um, but if we apply such things straightforwardly, mixed precision without loss scale, we can fail. But there is a technique which is called loss scale, which is targeting the loss function, and we multiply loss function to some small number. Well, yeah, too big number, which is power of 2, and we save such computations. But first, let's talk about so-called half precision arithmetics. So if we talk about low-level number representation in computer memory, we have so-called mantissa or fraction and exponent. So fraction tells us which number, so which digits do we have in this number, and exponent says us about scale of that number. So which power of, well, usually 10 we have for that number. And we also have sign. Well, actually power of 2, of course, but it's more kind of convenient to use 10 for human interaction. And these numbers can be normalized. They can be from 2 power minus 14 to 2 power 15 because we have 5 bits. And they can be denormalized. Denormalization works for very small numbers. This is the case when not only the exponent is the lowest one, but leading numbers here are zeros. So we try to fix exponent over overwhelmed exponent is fixed by digits in fraction. So if we talk about numbers, so maximum is 65,000 and minimum is like 10 minus 5, something like that. But actually for neural networks, we don't need denormalized numbers. And in PyTorch, by convenience, all denormalized numbers are getting zeroed out. So if we reach that minimum, that one, then we just assign it to 0. So this is what half precision is. Well, the structure of the number is the same for other types, for 32 and for 64, the same, but numbers are bigger. And for half precision, yeah, so this is it. And let's look at this. So to understand what is loss scale and why do we need it, let's look at diagram of gradients during model training. And we can see that many gradients are almost 0 or around 0, so kind of denormalized ones. So we can, even if it is not equal to 0, we can assign it to 0. And others, they live here. And you can see magnitudes here is from like minus 36 to minus 21, maybe minus 19. So quite small things. And to work with them, we have, so in FP16, we have representable range here. So from minus 24 for denormalized, yeah, from minus 14 to 15 in case of usual numbers, and from minus 14 to minus 24 for denormalized. And our gradients are smaller. So the idea is very, very simple. Let's multiply our loss function to some big number so that we will shift that distribution to the right, up to the upper corner of FP16 range. We will not use the norms, so we will have to stick to that thing. So here, let's say we can, so something, I think mode of this distribution is minus 27, okay? And let's move it to like 26 magnitudes, yeah, and so that this will go somewhere here and we will distinguish all the numbers we needed. So this is called loss scaling, and this algorithm is quite simple. So actually this multiplication factor have to change at each well, maybe not at each iteration, but in some range of iterations, because you realize that these gradient magnitudes, as we train model more and more, so model becomes better in our task, so that the absolute value of gradients will fall and fall and fall. So this is a natural property of gradient descent. So that this multiplication factor should be dynamic, right? And let's see what's the algorithm is. So first, it is already implemented in PyTorch. So first we maintain primary copy of weights in FP32 because we want to store the the network in this precision, and each time we make iteration, we make FP16 copy of that weights. Then we perform forward propagation in this FP16, but changing only to exception is only for operations which need FP32. We'll talk about them several slides later. Then we multiply by scaling factor, and we backprop through FP16. So we don't care because we use that scaling factor. We aligned our multiplication factor to current state of gradients. Then we multiply weight of gradient by 1 divided by s, so we put it back, and then we update the weights, but we update weights in FP32. So this is the algorithm, and the main actually despite we store model in FP32, we make all the intermediate operations, so activations in forward pass and gradients in backward pass. We store them and compute them in FP16. That's why we save, and all the computations and most of memory is used here at this stage, so that we save everything we can save, and no matter that original weight is in FP32. Then the question is how to choose a scaling factor. And for scaling factor, we can put it statically, but it's not correct answer. As I already said, gradient values will fall, and the full algorithm is the following, including choice of scaling factor. So first we initialize it with a large value with some usually power of 2 or power of 2, and this initial value have to be can be chosen by hand, so it's not a big deal. You can just make one forward backward prop on some batch, look at the magnitudes distribution of your weights as we did before, and just look at this number and make first attempt to put it to some relevant number. Then we have the same copy of weights, forward, multiplying, and so on. And we include one more step here, which is we measure number of infs and number of nonce in weight gradients, because sometimes this will happen because at least we have outliers or something, so it can happen. If we encounter such thing, we reduce s. So we say that we scale too much, so let's reduce it. And if not, then And also we skipped weight update, but well, it's kind of will take us more computations, but that's okay because we don't have gradients for everyone. Then we scale it back, and if there was no nonce or inths, we increase s, usually to power of 2. So this is the full algorithm for mixed precision operations with loss scaling. So we solved the first problem of that procedure is loss scaling. And the second point which we need to visit is so which operations should be made in FP16. And here in PyTorch, there is a sub-package which is called automatic mixed precision. What it does is it converts to float 16 where possible. So we will visit that formulation, and yeah, keeping float 32 master weights. By the way, in these weights, we can accumulate per iteration weight updates, or we can accumulate from multiple GPUs or even from multiple machines. So we do final operations over weights in float 32, and we use loss scaling. But what should we do to use AMP efficiently, and especially tensor cores of our graphical card? So first, we have to meet shape constraints. We already talked about that last time. Then we need to increase arithmetic intensity. So also something we talked about last time. And also we want to decrease non-tensor core operations. And happily, in contemporary neural networks, there is a lot of there are a lot of operations in neural networks which require a lot of computation. So for example, self-attention module, this is one great example where people achieved better neural network performance using bigger computational resources, parallelizable computational resources. So let's go through that points one by one. So we already said that for linear layers, we want 8 batch size 8. For FP16, for convolutions, we want input channels, output channels to be divisible by 8 as well. And you can remember that in VGG network, for example, which we was talking about in computer vision class. And okay, when we satisfy these constraints, our operations go better. So we have M, N, and K, and different meanings here. Yes. So if we talk about convolutional layers, we also have this model. Then about arithmetic intensity, let's see. First, we want to use so-called dense separations, so fully connected layers, transformer layers, and so on. And we want to prefer wider layers. Because when we use wider layers, we become more arithmetically intensive. And when we talk about non-tensor operations, we can think of the formula of speed improvement in concurrent computations, where we have fraction of time on parallelized part, and this part can be parallelized. And the second y is factor for, well, kind of scaling factor, so how faster we compute. And our final result is independent part, and part which can be parallelized multiplied by or divided by speed factor. So this is the thing. And if we talk about real examples, so we if we have speed factor equal to 5, then and half of operations can be parallelized, we can see that the final number is factor of speeding up is 1.67. So not that much. Considering 5 times faster parallel operations, this is not very big. So it depends on the fraction. That's why we want this to be minimal and we want this to be maximal. One thing which helps us is batch size, definitely, and the other is arithmetic intensity. And if we talk about layers which can use mixed precision, well, which can use lower precision, we have 3 groups: LO list, denial list, and infer list. LO list is convolutions and fully connected layers. They are really efficient. And denial list is some large reductions. We can think of maybe um, average pooling with big factor. Then losses, especially cross entropy loss, so it requires more precision, and some exponential units such as softmax, such as sigmoid, and other involving exponent, because that operations also are very sensitive to precision. And if we talk about simple element-wise operations, so we can think of ReLU as the most widely used operation. It is inferred. So what is inferred is that system uses that type of precision, which is faster for that operation in that circumstances. What does it mean is, if we have previous operation in, let's say, FP16, we can use it as FP16. Or if we have operation in 32, then we can use 32. So it's actually doesn't matter. So it's better to choose the one that is faster right now. And by the way, there is a full list of such operations. So actually, every operation is marked to be in one of these categories. But actually, in neural networks, we don't need all CUDA operations, but still we need them. If
Can
we
you
talk
explain
about
what is?
uh-huh.
Yeah, I have a question. What is an override?
Override,
Mhm.
override what?
I mean, the link, it says functional overrides.py, and I was just wondering, what is that?
Name of the file. Well, it's internal AMP in enum. So it's just so way to program that. So I mean, the it contains just what it says. So functional. So overrides that are made in a functional way. So
I mean, I understand. So this is allow list, the things that are allowed, I guess, deny list, and then infer list, and then functional override.
no. These are no. This is just list which marks every operation. So you have functions for FP16. This is convolutions and linears. You have FP32. So it just lists of operations. So like soft plus, log softmax or softmax should be done in FP32. So it's just lists of operations, nothing more. And the name of the file, well, they wanted to name it this way. I don't know why, actually. I don't no, I'm
Yeah,
not
because
that deep.
usually override has like a little bit different meanings, so that's why I was asking.
Okay, I don't know. Kind of default for I mean, override is override. So I mean, it's a technical detail of implementation for that thing, and it depends on their architecture how they do that. And because I don't know their architecture, it can be called anything. I think.
You got it. Thank you.
More than that, they can have their own notation of something. So I mean, it's very hard because it's a big project which I'm not contributor of, and that's why I just don't know.
I just had a quick
Okay.
look in the code. Just had a quick look
Mhm.
at the code, and looks like this overrides is just the way they say it's the way to force either FP16, FP32, or blacklist basically. So it's a forcing way, right? So this is why it's override. I guess it's kind
I
of
don't know.
just the kind of English. I think it's just in the comment what they say. So force either FP16 or FP32.
Yeah.
Got
So
it. Thank you.
for different so yeah, I mean so uh words which people use to demark uh, different entities depending on the project. So I don't know. I don't know why they use that name. Just don't know. Okay, so if we talk about hardware part, we need tensor cores, but it is there starting from GeForce 2000. So now it's 4000, almost 5. And the corresponding Tesla models, so that you always have it. And if we talk about some about success stories, let's say, we can see several neural networks. So let's see at UNet, for example. It's okay, it's a 10% speed up, but almost for free. So it doesn't and we don't sacrifice the quality. That's why we can use that much. And for different networks, you can see there is different speed up. So for ResNet, for example, they have 3.47, so quite big thing, and sacrificing not even a percent, so kind of 2% of quality sacrifice. So it really well, it's better to use that thing. Happily, in PyTorch, the algorithm of AMP is already implemented. So you just set up the flag for AMP to true, and that's it. They have they have in AMP in PyTorch, they have automatic translation of layers. So they mark it themselves based on the rules which I shown you. Actually, you can do that yourself. You can provide explicitly set of rules for your layers, but for big neural networks, it kind of may be a problem. I mean, just in terms of the work, amount of work to be done. That's why I think like 80 to 90% of speed up will be done automatically. But if you really want to speed it up even more, you can make it yourself. Thinking of what's better, but it really, I don't think it's a good way to do. So I don't recommend actually. Let's look at so performance limitations, like let's calculate arithmetic intensity. And arithmetic intensity actually depends on two factors: time which we spend accessing memory, and time which is spent for computations. And if we have a highly parallel architecture, which can be, well, parallelized easily as NVIDIA GPUs, we have a final time as maximum of these two. Why is it maximum? Because we may start to call memory first, and then we can start operations. And if these two times match, we can plan all our operations one by one. So we have many operations in sequence, right? And even if we shift computations and memory loading, we still can cover all the timeline, so that usage of arithmetic cores and transistors will be maximized. This is our kind of ideal world. And if we talk about some estimates in numbers of that things, so time to access memory is number of bytes which we need, and divided by bandwidth of our memory. And for math, we have the same, but number of operations, so floating point operations, divided by bandwidth of our computational cores. And let's see, if we have a number of mathematical operation, well, intensity, computational intensity bigger than memory, then we can well, actually we can compare everything with one constant. So for our problem, we can divide number of operations by number of bytes required for that operations, and compare it with a constant, which describes our hardware at the moment. And here, yeah, number of operations by number of bytes is arithmetic intensity. So for 100, this bandwidth math by bandwidth mem is something around 40. So this is a constant for a 100 architecture, hardware architecture. And let's see. We have two types of memory: on-chip memory, so this is GPU memory, and off-chip memory, this is RAM. So usual RAM when you put CPU to device. For on-chip, it is 3.1 terabytes. For off-chip, it is a bit less than terabyte, and the amount of operations is 125 FP16 teraflops. So this number is around from 40 to 140. And if we talk about efficient operations on that architecture, we need to keep our operations arithmetic intensity in that borders, actually. And yeah, also we have to arrange operations. So it's better to arrange operations in the way that we have more computational intensive operation than less, then more, then less, if we have such opportunity. So this will be the best thing. And let's consider fully connected layer. We will have 4096 as input, 1024 as output, and batch size 512. So number of operations is in by out by batch size by 2. By the way, why is it by 2?
For propagation and back propagation?
No, no.
Sorry, I guess it's written in the slides, since we have two operations like multiplications and accumulation.
So what is the second one?
Accumulation.
And what is it? I don't know. I mean, I know operations, mathematical operation. I know taking exponent, taking square. I don't know default mathematical operation of accumulation. What is it?
This is a sum. When we store, when we do sum and store back.
Yeah, that's it. So we multiply matrices, like we take a row from one matrix, we take column from the second matrix, and we compute dot product between two vectors. So first we multiply coordinate wise, and then we sum everything. So that's why we have two operations. So number of multiplications, pairwise multiplications, and then we have to well, here it is called accumulation, but actually it is just summation, right? Okay, that's why it's 2 by batch size in plus out. Actually, we don't count bias term here, so actually we have to add batch size by output, but it's really usually small number. So compared to input, which is 496, it will be bigger by 1, but it doesn't really matter. So it will be 4 10 power 9. Then if we talk about weights, we have in by out by 2, inputs batch size in out, and output batch size out 2. And overall, we have only 0.01 power 10 power 9, and it is for 400. So such linear layer is bounded by computations. That's why we don't want to optimize it more. In that situation, you can even make batch size smaller, for example, if you need it for any reason, without sacrificing efficiency. And that's why contemporary neural network architects, let's say, so researchers prefer bigger layers, because they use hardware better. Also, let's apply the same computations to ReLU, and we will see that it is 0.5 10 power 6 megaflops. So it's 10 power 6 megaflops, and so 0.5. And for memory, which we just need to store input and output, so very small input and output, so that arithmetic intensity is quite low. That's why we see that this operation is bounded by memory, because we need to read and write more than compute. Yeah. So all operations can be computed in that way, and if you see some also there are instruments for automatic counting of that things, or automatic estimation. It's not very hard, as you can see, and such analysis can help you if you search for optimal state of your neural network architecture. So yeah, let's look at the linear layer, and let's say which minimal batch size will provide us great performance, so high arithmetic intensity, and it is around 42. So the thing is that actually you want your memory and computation to be of one order of magnitudes, because you don't want one to be bigger or another to be bigger. You want everything to be in harmony, let's say. Okay. And so this is all about computational intensity in that stuff. So let's talk about TensorRT. Actually, when we infer with neural networks with already trained neural networks, we have a lot of differences in everything, in environment, in batch sizes, in what we compute, how we compute, and so on. So usually for neural networks, well, for machine learning models generally, people try to infer more than train, because otherwise it would be like not very efficient. And despite despite your training process, if you have production for, I don't know, at least several millions of users, your model will be used more time than you train it, because it is done in highly parallel manner for every user. That's why it's not very that's why your training time is not very big, and we need to optimize model for inference as much as we can. So let's see how it works. So NVIDIA provides their own engine for computationally efficient transformations of your model, and it is called TensorRT or TRT. First, you train your model, then you got an artifact, and you provide batch size, you provide precision. Sometimes you can provide a data set on which to optimize that. Then TensorRT engine optimizes it, considering all the information you input, and then they generate so-called planned, compiled TensorRT model, which they save to disk, and then you can validate it. So you can compare original neural network with what you have now and estimate that everything works well. What does TRT do? It's quite simple things on the one hand, but on the other hand, the engineering implementation of all that requires a lot of precise code and so on. So if we talk about in-trained neural network, we have several operations for each stage. And so here you can see inception architecture, and TRT can glue some layers together. So, for example, if we have 3x3 convolution, then some bias, we can add that bias to convolution and don't apply it. And also we can use, for example, ReLU as the final. So there are so-called piped operations, which can be done faster. So when you know that you do the same operation on the same data in place, you can send that operation before. So it's a processor pipelines and so on. So they what they do is they form blocks of such operations. It is called vertical fusion. The same can be done, for example, with dropout, because when you use dropout in training, for inference, you have to multiply by a constant, 1 divided by 1 minus p. And you can also multiply your previous linear layer, let's say, or next previous layer to that constant. And there are many such improvements. The next thing is quantization. You can use int8 for inference, and that's no problem with that. The only thing is to make correct quantization. And if we talk about neural networks, you want to preserve linear operations over your quantized values. That's why you want uniform quantization, so you don't need to make it by quantiles. And if we for inference, usually people use int8, which is from 127 to 100 minus 127 to 128, and we have to choose the level, a range of this quantization and the step of quantization. Usually in such engines, so in TensorFlow as well, they use some sample batch size. So they input some batch into your model, then they look at distribution on each layer, and then they compute scales at which they want to quantize it. So this is how it's done. We'll see that in practical part.
Is this a distribution of sorry? Is this a distribution of parameters, parameter values on each layer, or
values? I would say values of outputs. So if you have inputs and outputs, actually that thing. So what do you want to do is you want to compare. So you have three things: distribution of inputs, distribution of weights in your model, and distribution of outputs. And you have to kind of match them. So that's it.
Yeah,
so for
thanks.
each of them, you want to make quantization. And if you do that uniformly, then you can multiply integers and end up with integer as well, but from other scale. And after such quantization, you want to check that your model gives good enough results, and you can preserve, for example, validation set for that and use it, or test set maybe. Also, there are techniques which are called quantization-aware training, which takes in train time for the model, it performs this fake quantization. So when you have your inputs, you convert them to, so you quantize them, you dequantize them, and then you train a network. And you can do that on any stage, actually. So this is called quantization-aware training. It is used, I know people who research on that topic, but I can't say that it is widely used nowadays. So in most cases, just usual quantization, so static analysis and quantization is enough to save most of the most of the quality of the model. That's why it's more research thing. Okay, so here are some links, and let's go to the next point, which is so the next stage after you performed preparation for deployment, you want to deploy your model. And here, the next instrument comes to game, which is called NVIDIA Triton server. What is that? It is a web server which is capable of running your neural networks in it and handle everything connected with that process, including batching, including reshaping, packaging, the usage of different types of hardware, and so on and so forth. So everything you need for inference. So this can be characterized in one phrase. So if we go to points, then Triton is enterprise grade, really stable and secure solution. It has concurrent model execution batching, which we will talk about. Also, it supports a lot of frameworks to infer. So the inference server itself is a set of algorithms over input data and how to put it to hardware. And they support a lot of backends. So for example, it is TensorRT, of course, it is ONNX runtime, it is OpenVINO, it is just CPU thing. Also, they give opportunity to write modules in any language you like. So it's C++, Python, Java, Go, so whatever. Also, they include live updates. What does it mean is when you put a new version of the same model to the server without rebooting the server. So you can update your model in production. As I said, it uses a lot of backends, so both for CPU and GPU, and also supports many instances of for the same model. So sometimes you want to provide back compatibility for your service, and that's why you need to get previous version ready, at any time. So you have to store it in GPU memory if you infer on GPU, or in RAM if you infer on CPU. As already said, yeah, arbitrary function execution on many languages, and modal ensembles. One more great feature is modal ensembles. So let's say you have some I don't know, OCR plus some language processing with LLMs. You can write them as separate modules, and then you just plug them into each other. It can be done with Triton Inference Server. Yeah, it is also widely supported by community and by many enterprise solutions, so cloud solutions and so on. So these were some words about this Triton Inference Server. Let's go a bit deeper into that. And so they have documentation. They have it is open source instrument, so you can check out the code. It's quite popular, and it's written in C and C++. Actually, if we talk about especially neural networks inference server, I can say that it is the only one option, because actually you have like Seldon based, or maybe MLflow serving, and many other instruments, but such high level instrument and very powerful instrument as Triton, well, no one can provide anything compatible. Anything comparable. Okay. That's why it's the #1 choice if you want to serve your models. And also Triton is able to serve gradient boosting as well. So they have fast inference trees library, something like that. So you also can convert boosting algorithm into on NX into TensorRT and run it on GPU as well, not only neural networks. So let's look at the architecture of that. They provide HTTP interface, and they provide gRPC interface as well. So for production, for high load, of course, it is gRPC. For casual usage, it's HTTP. It's very very flexible and user friendly. They can have model repository, so maybe usually something like S3, and then they have internal APIs. They have all the queues, schedulers which needed. Also, you need to provide some drivers and so on. And from that thing, it can use all the computational resources you have. Also, Triton comes with a default set of metrics for that server. So health check metrics, like starting from temperature on each computational block, usage of memory, number of input requests, output through, well, kind of throughput, latency, everything. So this is how it works from bird's eye view. And let's look at batching and concurrent execution. So let's compare several setups. So if we have inference server, we can have several inputs, then one more input, and several more of them. And let's see how it's yeah. So it can arrange a number of parallel executions, considering number of compute units on your hardware. We will look at this a bit later when we'll talk about batching. For TensorRT, they have fixed format for model repository. So they have model name. So there should be a top level model repository path in each of them, and it contains folders with different models. So in each model, you have model name. Then main config file is config pb.txt. I don't know why such weird format, but okay. Then for each version, which have to be integer and only integer, unfortunately, you need to put a model definition file. So one more configuration for the model and binaries for weights. So this is a overall structure of that model repository. And if we talk about module configuration, we can choose so-called platforms, so kind of backend. In this case, it is TensorRT. Then max batch size for that model. You have to describe inputs, their names, types, and dimensions, and you have to describe outputs. So this is configuration for one model, and we can have different different ways. We have different ways to set up batching. So first of all, we can put max batch size to some number, and this will be the fixed maximum batch size. But if we put it to 0, we can put that number to dimensions of our inputs like this, or we can, and in this case, kind of batch size will be fixed. So it will be just 8 and not more, not less, only 8. And we can put -1, which means any, arbitrary number, just like we do in Python. And this means so any batch size you like. Depending on your model, you may want to provide different strategies for that, because some models work well only on bigger batch sizes. For some models it doesn't that much. It doesn't provide that much of difference, so that you can decide. Also, you can enable in place reshaping, which is adding empty dimension. If your client sends you one object, this object will be shaped without. Sometimes it can be shaped without explicit batch size dimension, and for your users not to be bored by such situation, you can enable this extension to inside inside Triton inference server. So this is one more thing. It has all the data types we need. And here is the comparison table to different libraries, but actually, well, we have everything we need, so that's all. I think nothing more to say about that. And one more thing is version policy. For kind of as a default thing, you can use all, but for all, as I already said, you will have to spend amount of memory for all the models to be presented on the GPU on the moment. So that if your model is 2 gigabytes, for 4 versions, you will have 8 gigabytes spent for models. That's why you don't want to support all the versions all the time, but you can set it up more flexible, like latest 2 versions of the model, or you can use explicit versions, so number 1 and number 3, for example. In both of these cases, you will spend twice more memory on your device. And version policy is also in pb.txt file. Also in Triton, you can set up so-called instance groups. So what does it mean? It's how many instances do you have on your Triton inference server? You can set up kind, so kind GPU if you use GPU, or CPU for CPU, and number of copies which you want to have. Or you even can run it on different GPU. So for example, on GPU 1, 2, you want to have 2 models, and on GPU number 0, you want to have 1 model. This can be used for quite flexible setup. And so you can imagine, like, you have some priority channel and you have general channel. So for some VIP users, you can go to separate channel every time, just to make it to provide best experience for your users, for example, for subscription, or I don't know why. So this is how you can use it. It's very, very flexible. Yeah, and my lovely thing is dynamic batching. If you enable it by default, it will use dynamic batching without delays. Also, you can put some delay. What does it mean is that when someone sends you a data to infer, you first wait for that delay, and then you start computing. But if in that time period someone else comes and also asks to infer that model, you can have batch of these 2 queries. And because your graphical card can process 1 batch and 2 batch if they are not 2 batches if they are not so big by the same time, so that you will spend less computations on that. And actually, this is a way to provide better throughput, sacrificing a bit of latency. But sometimes it can both save latency and throughput if you didn't do any dynamic batching before. Also, you can set up preferred batch size. So, for example, some models are more efficient on that sizes of batch. So Triton will try to form batches in that numbers. So how does it work? Let's consider some practical situation. So here is the time from 0 to some x. First, we got 2 queries A and C. Then we got query B, and then we had query D and E. So this is the input. And we can look at the what happens. If we don't have dynamic batching, we first process A and we put C to wait list, then B, then D, then E. So nothing surprising here. But with batching without delay, we can batch A and C, and also we can batch B and D. So let's think that in this example we have maximum. Okay, I got it. It's I I think. Let me see. Yeah, so let's say we have maximum batch size is 8, so that we can group A and C, and also having B, we can group it with bigger one, which is D. So it goes here, and the last one will be E. And you see that actually both latency and throughput increased in that case. But if we include dynamic batching with delay, we can process that 3 at the same time and then these 2 together, so that overall throughput is even higher. But if we measure latency for each, so for A and C, with delay, latency became bigger, and for B and D, okay, for B, it became smaller, and for B, it became bigger. And for E, it became smaller. So, okay, overall, maybe not a big difference, but you can see definitely that throughput is increased. And if you facing constant input signal, that batching will save you a lot of computations and a lot of latency and throughput. So very, very nice thing to use. And things become even better if you use several instances, so that it can arrange different batches to different instances. So this is how it works. One more great feature of Triton is ensembling. If you have building blocks of your final solution, you can bind them together by configuration file inside Triton Inference Server, and you can update each part independently and work with them as a separate, but have some this ensemble entity to deal with them together, all together. So for example, you can input image, pre-process it, and then you can put it to segmentation and classification. So actually, this type of problem I would do in one neural network, but it doesn't matter. You can. So for example, when did we use it is when we had a video. We had 3 inputs. So we wanted to build a content model, and we have to use all the content we have. So we took video first, we took image, so thumbnail or preview, and we took text, so title and description. Title and description went to BERT model, so pure textual model. Image went to visual transformer, and video went to frame BERT. And then we aggregated that 3 vectors into one, and this was output, so only one output for 3 inputs. So this is another example of model ensembling. And of course, we train that model separately because these are different data types. Yeah, this is the thing. As I said, it supports a lot of backends. So TensorT, TensorT-LLM, ONNX, TensorFlow, PyTorch, Pavina, Python Daily. Yeah, Phil, it is called Phil, Forest Inference Library. you can use it for boostings, and also you can code your own backend if you want to. It also has a lot of other properties which we will not cover. It is covered in documentation, and it will be useful for you for advanced usage. Yeah, so here are some links for that. You can go and read if you want more things. It is done as MD file based documentation. So this is it. So most of the images are taken from here. Yeah, so that's it. Yeah, by the way, I need your topics for projects, and also I think I will need the code as well, so we can discuss it. So yeah, I have to make a form for you to submit your proposals. Okay. So, and next time we will convert neural network to ONNX and TensorRT, and we will set up Triton inference server with. So that's all from my side.
Okay, so next time we'll have the code ready, and we can do that actually on Triton. I mean, to deploy the model.
I will show you how to do that. Yeah.
Okay, got it. Good. Thanks.
An example of one neural network. Yeah. Okay.
Thank you.
Thank you.
Yeah, thank you. Goodbye.
Bye.
Thank you. Bye.
Thank you. Bye.